Hi, I'm Ken Stafford, and I'm here to talk about one of my favorite subjects, which is the study of forces and the way it works in mechanical systems, especially useful as a fundamental background for robotics engineers and mechanical engineers. Before we get into this, I need to talk a little bit about what static analysis means. Eventually, in a continuing set of videos, we'll talk about applying this to free body diagrams and equations of equilibrium. But right now, let's look back about the very fundamentals of force analysis. We all have a sense of what statics means, but most of us think it means not moving. In our terms here, and what I really want to stress here is that if you think about static equilibrium, which is very, very useful, it's not about not moving, it's about not accelerating, or at least having very trivial accelerations. From the very foundations of physics, we understand that Newton's is one that said, of course, that force equals mass times acceleration. Now, the beauty of static analysis is that if the A goes to 0, well, then the sum of forces must all equal 0 as well. Now, is that very useful? I mean, do we think we're really in static equilibrium? To get a grasp of what I'm talking about, consider the fact that I'm not static as I talk to you here today. I'm actually moving about the speed of sound eastward due to the rotation of the Earth. On top of that, I'm also moving about 70,000 miles per hour based upon the rotation of the Earth around the Sun. And additionally, the Sun itself is moving about 450,000 miles per hour due to the trajectory within its own galaxy. So when you add all this together, we're certainly not in a static, non-moving condition. But I will maintain that relative to the surface around me, my desk, my chair, the accelerations are fairly trivial, so therefore I'm going to assume that they go to 0. On an aligned notion, however, we need to consider things other than linear accelerations. What about angular accelerations? And angular accelerations are also important to consider when you talk about statics. Certainly, as there is F equals ma, there's an equivalent equation for spinning accelerations, which would be the torque equal to the moment of inertia times the angular acceleration. So for true static analysis, we need to consider both angular and linear accelerations, and they relate to torques and to forces. One other comment about torques that I must explain here. First off, if you look at this example of a wrench, we know what torque is. We kind of intuitively know if you put force across a distance, it ends up being a torque. Now, in terms of engineering, we often call that torque a moment. Not to confuse the issue, but moments are used for a lot of things. It really means some entity applied over a distance. So technically, the moments that we're talking about are force moments, but they're interchangeably, we're going to call them torques. When we look at both forces and torques, to analyze them, we need to understand that Newton's laws, force equals ma, is actually a vector equation, which means that if we are going to analyze these, we need to break these down into some sort of a coordinate system. If you take these vector equations, you would understand that in 3 dimensions, you would have x, y, and z, which means the sum of forces then could be, if you wanted to analyze them carefully, you'd have to look at the components in each of those 3 directions. Similarly, of course, if you have forces in 3 directions, you can also have twisting efforts or moments in 3 directions as well. So the general form of static analysis would include 6 equations. But practically, many problems, in fact, all of them in this course, in Robotics Engineering 1001, can be looked at as if the forces were all in one plane. And so if you think about traditionally the forces being in the xy plane, then you only have 2 equations of forces to consider. So now would be a good time to understand and think about the relationship between these force directions and the resultant moment directions. Again, this is should be a review for you, but let's think about these in terms of the right-hand rule. We need to establish the positive sense of x, y, and z. So if you hold your hand like this, with the first 3 fingers in orthogonal directions, you would find that the thumb, by normal convention, would point in the positive x, the first finger, the index finger, in the positive y, and your third finger into the positive z. Now, a lot of problems can be reduced to forces in two dimensions, forces and displacements in two directions. For example, let's say a typical condition would be an XY plane series system of forces. The question is, where do the moments that result from that exist? Now, in terms of forces, it's quite clear that the arrow, the vector, would point in the direction the acceleration would occur. But when you have an angular acceleration, it's not quite as clear. So what I want you to understand is that you can now use the right-hand rule in a second method. First off, we used it for establishing the coordinate system, positive senses, but now let's look at how that works with moments. So let's say that we have forces and distances in the xy plane, and we see that those forces would cause a rotation. They could cause a rotation if the torque was unbalanced. We have a force times a distance. If we curl our fingers in the direction that rotation would occur, the angular acceleration, then our thumb is going to point in the sense of the vector which represents that moment. Now, understand that the thumb then is actually going to point in the axis of rotation of that acceleration, angular acceleration. It's simply a mathematical contrivance. It could just as easily have pointed in the other direction, but for consistency, we're going to use the right-hand rule that says that in our xy plane, in this particular example, a counterclockwise rotation then would be a positive z direction. Now let's return to the wrench example and see how that applies. So in this wrench example, we need to look at the angles and the directions of the forces and the resulting moments. So if you take now the rotation around that wrench, you will see that it would turn counterclockwise in this example. Your thumb is coming out, which is in the positive z direction. This is a very important concept, and it's something you need to really be careful with because you will make mistakes on this. A final concept we need to review now before we get into the total utility of free body diagrams is this concept of friction. We all understand friction. We all understand that friction is the coefficient of friction, mu, times normal force. But here's something we need to understand. For example, me sitting here, my combined weight with the chair and me is about 200 pounds. And I assume that probably with these rollers and my feet on the ground, I probably have a coefficient of friction of maybe about 0.2, which means that if we use the friction equation, we'd find out that the force of friction on my chair here, which should be orthogonal to normal force, should be 40 pounds. But the question is it? Because if I did have 40 pounds going in one direction, I should be accelerating that way. So my point is that we need to be very careful about the force of friction. It's going to be equal or less than mu times normal force. In this case, when I'm stationary here in this chair on level ground, the force of friction is actually 0. The only time it actually equals mu times normal force is when the surface is skidding. In other words, it's friction limited. Armed with these basic understandings of Newton's laws and friction and the coordinate system, now in the next videos we're going to go on to how to put these into real systems through the equations of equilibrium brought about by free body diagrams to solve really complex and interesting problems.